Okay, good. So again, it's in the meter number 2, you won't see that like a 2-parameter systems. Okay, then what happened actually in your null space? In your parameter space, you actually have 2 parameters then. For example, right here, if x1 to xn is normal, right? Normal. Then right now it's both of the mu and the sigma square are unknown. That means if both are unknown, you need to deal with that, okay? But in the hypothesis, I'm only interested about testing what? Mu equals mu 0, or mu doesn't equal mu 0. So that means whenever I do that, whenever I have 2 parameters unknown, okay, even though I only do hypothesis testing on 1 parameter, the other guy, because it's unknown, you still need to estimate it, but based on different parameter space. That's a detail. Okay. So again, it's even I find the LRT lambda x, even I can write everything to the same supremum theta in the null space L theta, and then supremum theta in the oval space L theta. By writing, it's still the same, okay? But the null space become what? The null space, because of 2 parameter system, you need to have mu equals to mu 0 because of null space. And then your sigma square is still free. They are still something you need to deal with because they are unknown, okay? Then oval space, of course, there are no limitation. Mu equals to the real line, and then sigma square is positive, okay? So it means, again, it's by writing, by definition, or by principle, LRT still do 2 things, okay? So one find the maximum, one find the MLE under null space, one find the MLE under oval space. Then what will happen? Find the MLE under null space, okay? For one, mu equals to mu 0, actually it's fixed. You don't have to do anything, but you need to find MLE of sigma square, okay? I'm not going to do every details, and you know that personal already, okay? So if you do have questions about why the MLE look at that way, you let me know, okay? First, it's remember, if we do MLEs on sigma square, okay? We always say MLE of sigma square is what? 1 over n, summation I from 1 to n, xi minus x bar, then taking square, right? The reason for that is you might not necessarily know what mu is. You plug in sigma square. You plug in your mu by x bar right here, okay? But right now your mu is actually mu 0. So if we really derive your MLE, okay, read by that principle about, you know, solving that joint PDF, right? Solving that joint PDF right here. If you do solving that local function or joint PDF, you would get your MLE actually is what? You plug in your mu 0 with x bar right here. Okay, good. So that means under null space, your mu sigma square, you do know mu equals to mu 0 as fixed. It's fine. But you still need to solving for MLE of sigma square under null space. Right here, we put theta not, okay, equals to xi minus mu. Pay attention to that, okay? And then if you do have the mu, if you do have the mu 0 hat and then sigma square 0 hat right here, then you plug in back, right? So you know what I mean? So you have this kind of mu sigma square, right? By joint PDF, 1 over n, right? You have everything is the same. Everything is the way you will learn from the normality, right? everything is standard drill. And then eventually you plug in your mu hat, sigma hat into the joint PDF of the mu hat, sigma hat is right here. Okay, everything looks the same, and you will find out it's this term right here. It will cancel a bunch, then become minus n divided by 2. Okay, good. I'm not going to go through it in detail. Okay, you try it a little bit, and you will see that that's what happens. Okay, then of course this guy would say something. Okay, so then you thinking about your denominator for lambda of LRT. It's based on overall space, right? Based on overall space, everything's free. The same thing we talk about. Actually, mu hat is x bar, sigma hat is what? The same thing as we talked about before, right? Summation I from 1 to n x minus x bar squared divided by n, not divided by n minus 1, divided by n. That's MLE. When your polymer space are free. Okay? Then again, it's you plug in back about, I'm going to plug in back mu hat and then sigma hat. Okay? Using these two guys. Okay? Then you'll find out your exponential term is going to cancel a bunch as well. Then minus n divided by 2 remaining. And then this guy is you plug in theta hat square. It's okay. So again, everything is standard drill, right? As long as I can find, as long as you know what my null space is, as long as you know what overall space is, and then on the null space you find the MLE. On the overall space you find the MLE. Okay, that's what LRT means. Whenever you have that, you take a ratio right here. And it's not hard to imagine, right? You do have this guy and this guy cancel out when you do ratio. And then become ratio of this guy and this guy. Right? And then so it's not hard to imagine you have this result right here. Okay? Good. And then since you have that sigma square, this guy plugging x bar, and then sigma hat 0 square, this guy plugging mu 0. Okay, you can go in back to see what you have right here, right? One is plugging mu 0, one is plugging x bar. Okay, good. So then, now how to find it here. Okay, it's lambda x. Okay, again, you will face in that situation is what? I do have my LRT told me that I need to find that it's smaller than C, right? That's a typical LRT. But your lambda x is so complicated. Your lambda x is not easy to evaluate what kind of distribution your lambda x is. Maybe you would, maybe you don't. Okay, but to me, it's not really straightforward. You will know that what lambda x follows as a PDF. Okay, then we will do the same drill then. Hey, do I have anything that's easier? Okay, maybe it's MLE, maybe some easy statistic T right here. Then I evaluate much bigger than C star or smaller than C star or both maybe. I don't know which one. It's more likely you guys are experienced enough. You might tell it's actually two tail, right? Because null hypothesis is two tail, alternative hypothesis is two tails, right? So you might imagine that it's eventually it would be bigger than C1 star, or actually C2 stars do that. Bigger than C2 star or smaller than C1 star, right here. Okay, good. Then things become tricky then. The way I say tricky is this. Look at your lambda x. You really have no idea where to find that easy statistic T. Okay, so let me give you something as an answer. then you ask me, it's how do you know that? All I can say is I just know that. Okay, good. The reason why that is because I do know whenever you look at this test. Okay. Imagine this is okay. Imagine not using LRT. Imagine you're undergraduate student. You look at this testing. Okay. You look at your mu unknown, sigma square unknown. And you look at this test. Tell me what test you are going to use. What test? Two sample t-test. Right? Okay? Because I don't have mu square, then I need to replacing my mu sigma. So I'm sorry. Because I don't know about sigma square, I need to using my standard deviation, or I need using my sample variance or sample standard deviation to plug in the denominator of my z statistics, right? Remember that? I don't know if everyone know that or not, but I just said it. Maybe when I'm undergraduate students, I know that. So I remember clearly about how to evaluate what test you are going to use, right? At the time, I would say that, yeah, because of I don't know about sigma square, I need to plug in. Whenever I plug in where my sigma is, about z test is, then it become t test, because distribution would behave like a t distribution. You will see that right here. Okay, so I know that, so I'm trying to make it that it's equivalence between your LRT and then t statistic. It's okay. Then how do I do that? If you know the direction, actually it's not that hard for you to evaluate. Only thing to do is what? Only thing to do is open up your, I think it's numerator. Let me make sure on that. No, open up your denominator. It's, sorry about that. By saying open up is what? By saying open up, it's you working on your summation I from 1 to n, then xi minus mu 0 denominator, then make it as a summation I from 1 to n, then xi minus x bar, then plus x bar minus mu 0, then taking square. It's okay. By doing so, you will say it's summation I from 1 to n, xi minus x bar taking square, then 2 this plus, right? 2 times x bar minus mu 0, then summation I from 1 to n, then xi minus x bar, then plus summation I from 1 to n, then x bar minus mu 0, then taking square. Okay? And you should know what I'm going to do. You should know this guy is what? Is 0. Okay? So make your denominator is what? Then make your denominator, let me see. Okay, I just write. Then make your, that's easier for me to write here, because then make your denominator is summation I from 1 to n, then xi minus x bar square, then plus. This guy right here, inside guy doesn't have n, so it's n times x bar minus mu, then taking square it's. Okay? You guys with me? And then I'm going to switch between numerator, denominator, and then I'm going to switch these two guys. Okay? As long as I switch, this guy, the power part is n divided by 2, then become negative. Okay? Good? Then as long as I switch, then I will be able to working on inside guy right here. Okay? Which means that it's, then the inside guy become this star sign divided by summation I from 1 to n, then xi minus x bar square. Right? I switch, My star equation right here is this. Okay, good. Then it becomes what? Then it becomes inside that becomes 1 plus n x bar minus mu 0 square. Then this guy is summation I from 1 to n. Then let me make sure that you switch 1 xi minus x bar taking square. Okay, then pulse n divided by 2x. Okay, good. Then let me put here n divided by 2 minus n divided by 2x. Okay, so then I purposely creating so-called t statistics. Okay, which eventually is this equation right here. X bar minus mu divided by s divided by square root of n. Okay, of course s right here, it's 1 over n s squared, 1 over n minus 1 summation I from 1 to n, then xi minus x bar, then taking square. Okay, I purposely creating a t statistics and then using that going back to this, plugging right here. Okay, it's going to give me 1 over n minus 1, then t squared. Okay, you can double check on it. You will see that. Okay, then the reason for doing that is I do know this guy follows t distribution. How do I know that? It's actually not hard to double check, because under null hypothesis, I do know this guy follow normal 0, 1. Right? This guy follow normal 0, 1 under null hypothesis. And then divided by what? Sorry. Divided by what? So I also know that it's, so I also write x squared equals to 1 over n summation I from 1 to n, then xi minus x bar squared, right? I also know that n minus 1 times x squared divided by sigma squared follow what? In the denominator, right? If you still remember, it's what? Follow chi squared n minus 1x. Okay? Then how do I make it up as a t distribution then? By definition of t distribution is what? I do a normal 0, 1 right here. This guy right here need to having square root of chi-square distribution, then divided by its degree of freedom then. Okay, good. So something I missed right here. This guy is actually is not sigma square, actually divided by who? Mu 0, I apologize. So this guy should be divided by sigma divided by square root of n. That's what's the derivation of the x bar is. Okay, good. By doing so, okay, this guy will still square root. Okay, so definition of t distribution is this guy z, this guy square root of chi squared divided by degree of freedom. Okay, you will find that it's theta cancel out, and then eventually become x bar minus mu 0, then s, then cancel out s divided by square root nx. Then follow t distribution with n minus 1x. Okay, good. So that means, well, you will say, yeah, well, I know the answer. Yes, I know the answer. So, and then I'm just trying to making that equivalence right here. Okay. So since you do know that t distribution right here, and the rest of that is what? The rest of that is how I'm going to find the equivalent region right here, right? Really is what? Nothing but you really draw that lambda x right here as a function of your statistic it's t right here. And you look at, sorry about that, let me taking out something, not necessarily critical. Okay. So if you really find that t right here, and really look at this function right here, and then we are going to evaluate. It's an increasing function, decreasing function, concave function, or convex function. The answer is what? The answer is not surprising. It's going to be concave function. How do I know it's concave function? First of all, it's t squared right here. It's definitely a quadratic function. Okay? And then whose power is negative. You basically know that it's a concave function. Okay? So then just using the principle lambda x smaller than c, again right here, okay? And then mapping to that equivalent region of the t statistic right here. You have what? Bigger or smaller one in terms of equivalent region. Actually, the same matching what you anticipated. You do have your lambda x smaller than c equivalent to either t bigger than c1 star. This guy right here would be bigger than c1 star or bigger than c2 star. Sorry, bigger than c2 star. This guy right here would be smaller than c1 star. That's exactly the same as what we did for only single parameter situation. Okay. Again, when we evaluate equivalence using graph or using no functional evaluation about a concave function, then when you find equivalence, how do I find right here? Nice, each base and the projection region. You do, but right now, so you don't have supreme amount to evaluate. Easy. Since you do know that t is going to be bigger, smaller than c. Oh, yeah, because they are balanced. Sorry about that. So, c1 star, c star, or t smaller than minus c star right here. Okay, because they are balanced right here. Okay, this curve is balanced right here. I think c1 star equals to c2 star. There's no much of argument with that as well. Then you basically just really divided them into two parts, right? Each of them give them alpha divided by half. Each of them give them half alpha, half alpha. Then you will find that C star is going to become, again, it's a distribution bigger than some quantile. Right inside it's alpha over 2. This guy right here, nothing but t equivalent minus 1 and alpha over 2 then. Actually, it's 1 minus alpha over 2. So I think I do, this is typo. They are using the right hand side quantile. So let me take out something out. Sorry about that. I don't know. This is actually typo then. So I meant to say it's actually it's right hand side probability. This guy should be beta. It's 1 minus alpha over 2, I think. Okay. Good, because I was using left hand side probability as a quantile, so I want to be consistent. Okay, then what does it call? Nothing but two sample t-test. Okay, so I meant to say is this: it's really so what I keep saying LRT is a general approach to finding a test. because using LRT, you basically could find a lot of testing, which is based on more intuitive approach, but you do have a kind of solid background to back up that intuitive approach, which means that it's LRT basically could using in any situation as long as your local function could be evaluated. Of course, if your local function cannot be evaluated, okay, technically because local function is not trackable. Okay, if you heard about someone say that, that means if your local function cannot be evaluated, then LRT is no use. But if your local function can be evaluated, then your LRT could be good use. Right now is what? Oh, okay. Do I say something wrong? I said two sample t-test. Yeah, it's two sample t. Oh, I mean, it's one sample t-test, not two sample t-test. Sorry, you only have one sample. So sorry about that. Actually, one sample t-test. Because you only have X. One sample t-test. I think some of you might know that already and make an error there. Okay. So, and I meant to say what happened to two sample t-tests then. Okay. So again, it's LRT could be used anywhere whenever you have one. Then the point it really is what's the null space, what is over space is right here. Say if x1 to xn follow mu x sigma square y1 to ym normal square, right? Okay. There are two things you need to pay attention to. One thing is this guy's sample size is n. Okay. Then the other guy's sample size is m. Okay. There are two different sample sizes. The second thing is what? They do have a common sigma square. Okay. So it's very important when you evaluate what is the null space, what is over space. Okay. And then of course x and y are independent. Then to do a testing about mu x equals to mu y versus mu x doesn't equals to mu y. Okay. Then mu x, mu y, sigma square are all unknown. Okay. But again, it's principle wise the same. So you should need to really evaluate what is my null space is. Okay. Then under my null space, what is my MLE is. Okay. Under null space right now is what? Mu x, mu y, sigma square. But you do need to have that constraint right here. Mu x equals to mu y. And then sigma square. Okay. Under oval space, there's no restrictions. Okay. Mu x, mu y in the real line, sigma square bigger than 0. Okay. And you write down that local function, L theta right here. And based on the what? Product of PDFs. But keep in mind, one thing is I from 1 to n. The other one is j from 1 to m. Different sample size. Okay. Then because of independence, I think you'll be able to write this local function in general form. And then the same drill. When you do null space, okay, you need to find MLEs. Find MLEs of what? Over what? Over your mu x got to equal to mu y. That means you only have a mu. That means you plug in mu right here. You plug in mu 0 right here. You plug in mu 0 right here. Okay. Then the whole local function become only two parameters. One is mu 0. The other one is what? Sigma square. And you're solving for MLE. then you will find out this is MLE for 0 hat, and then this is MLE for sigma square. This is not surprising, right? Why is this not surprising? It's not surprising because under null hypothesis, you do have your mu x equals to mu y equals to mu. That means this guy is mu, this guy is mu. That means what? X1, Xn, and then Y1 to Ym, they all belongs to the same normal distribution. That means that the same collection of data, that same collection of random variables. Then that becomes your sample size become what? M plus M. Then no wonder this is what? Actually what? Summation, total summation, summation, and then divided by sample size. Nothing but good. Derivation. The file is your sigma square is right here. Okay, plug in mu as a mu 0 hat. Okay, I'm not going to run through detail. Okay, if you derive it, you will see that. And then what? Then you plug in. Okay, plug in where that mu and then sigma square should be, replacing by mu 0 hat and then sigma square 0 hat. And you will find out again that your exponential part is going to be cancelled. Okay, then this guy remaining. Okay, but then you plug in your where the sigma square is, becomes sigma hat, sigma 0 square hat. Okay, so then again it's under overall space. Your mu x and mu y not limited, not restricted by any constraint. Okay, then you basically means what? You basically you maximize this, you maximizing this. Okay, to get mu x and then mu y, and then you become x bar and y bar. But in order to get it, you do need to maximize everything altogether. And then, but again, if you be patient, then you will find out your sigma square is this guy and this guy. Plugging x bar and y bar individually in a summation I from 1 to n xi minus something right there. Okay. Again, using the same drill, you plug in LRT, you'll find out this guy cancel a bunch. Okay, then this guy replacing by sigma square because sigma square replacing by sigma square hat. Okay, good. And then you found what? You found taking ratios, right? This numerator, this denominator, and you will find out this cancel out, and then this cancel out as well. Okay, and then you have that lambda x and y. Okay, will be so complicated. Okay, and then again, I actually doing the same trick. I switch numerator and denominator, then having their power right here become minus. The reason for that is I want to open up all these two guys right here. The same thing we did for one simple t-test. Okay, then you could double check my answer. You will find out this guy could be combined to become this. Okay, again, I have to say that I actually know answer already. I want to creating some t statistics when I do equivalence. Okay, then the definition of t statistics x bar minus y bar divided by really weird things in the denominator, especially this is so-called ported, piece for ported. Ported standard deviation or ported sample variance, right? Again, not surprising by this. It's what? It's something like, oh no, it's actually not necessarily surprising. I'm sorry about that. So it's actually need to You need to derive a little bit. There's no straightforward explanation on that sense. And then if you're solving that, you will think about it. This actually is divided by n plus n divided by 2. Okay, good. So I'm actually creating the two sample t-test you learn from undergraduate study. Okay, and then it totally making sense right here. It's my LRT is actually a function of that two sample t-test statistics. Again, what? Again, it's the same thing as one sample statistic. This can also quadratic function of lambda x of t right here. Okay, again, this guy quadratic, this guy give you concave. Okay, so then you're cutting down about C right here. And then you'll find that equivalent region, again, it's what? Bigger than something, then smaller than something. So again, this is perfect quadratic, so your C1 star equals to C2 star right here. Actually, you can use only one C star. Okay, if you're not aware of that, it's okay. You should give the half of that, then you'll find out that C1 star equals to C2 star as well. That's the central right here. So that means eventually this guy also time well. This guy also 1 minus alpha over 2. I still keep considering using left-hand side probabilities. Okay, you don't need to know that why this guy right here follows T, then the degree of freedom is n plus n, then minus 2. Okay, that's actually the same thing as one sample T tested. Okay, similar things. Okay, good. If you know that it's distribution n plus n minus 2, then you do know where to find this quantile to reject the null hypothesis. Okay, good. I'm kind of tired right now, so if you guys have any questions, feel free to slow me down. Okay, otherwise I'll keep moving. Okay, so then again, what if I have mu x and then mu y, and then my variance is not the same thing? How would you do? Actually, it's the same thing. To evaluate what's your null hypothesis, what's your overall space, and then deriving MLE really patiently. I have to say, really patiently for each mu x and mu y, for each sigma square x and sigma square y x. Okay, good. So I'm not going to do that in detail, okay, because it takes a really, really long time to do so. It's not homework. I'm not meant to say homework, okay. I may give you that. I still think about whether or not I'll give you this, okay. But if I want to do for fun, maybe I'll actually give you the homework. What happens if you have x1 to xn follow exponential theta, y1 to ym follow exponential mu? Okay. So if I'm doing testing about whether or not these two samples are the same, right? In the previous example, you look at two normalities. They are t-tests in some sense. But right now, you have your x1 to xn exponential theta. And then y1 to ym, remember that, exponential mu. I still have two samples. I have two samples follow exponential distribution. Could I testing about whether or not they mean are the same or not? You could. Okay? So eventually, you follow the principle of LRTX, you'll find out this is function of t right here. Okay? So let me ask you, if you saw t right here, what does t follows? If you are guessing what t will follow, you won't surprise your t is going to between 0 and 1, right? Because xi are all positive, while positive is way off. That means your statistics are positive divided by positive. And then summation xi is going to smaller than 2 sums together. Not surprising to see that t is actually from 0 to 1. How many distribution you have, you'll be able to see the domain is from 0 to 1. Either uniform or beta. Would you think this one's uniform? I don't think so. Okay, there's no information to tell me this should be close to uniform. This guy's beta distribution. And then you can go to Kassenberger. They will let you know your beta is alpha, and if two parameters is alpha and beta, and then what alpha and beta is in this situation. Okay, so if you have that t, if your lambda is in some function of t, then again that eventually still finding the equivalent region. I think right here I'm going to bet my bigger than C1 star or T smaller than C2 star. Okay, beta is not symmetric. Beta could be symmetric whenever particular alpha and beta is, I think, if I remember correctly. Okay, but if beta is not symmetric, then you find different C1 star and C2 star to reject the null hypothesis then. Okay, so these guys are all complicated. I can even share with you even more complicated LRT, but I think this is enough. Okay, good. But yes, I only want to say is only one thing. It's LRT is so general. You could actually using if you have new questions, you don't know how to do. There's no common testing you were able to go with. Okay, your question is new, your data is new, distribution of your data looks like really weird in some sense. Or maybe by the question itself, you do need to develop new testing procedures to testing anything of your interest. Then LRT is your good starting point. Okay, of course, you need to write down the correct equal function to get the LRT running. Okay. Good. Let me spend the last final 10 minutes about, hey, LRT is really complicated. Okay, in some sense, really solid but complicated. Oh yeah, yes. Yep. Did you talk to me?
Yeah. If you could just go back to slide 13.
13. Yep.
Okay, that's good. Yes. Thank you.
Okay. Yeah, that's fine. It's fine. Yeah, I might, I think it's lagging right now, so I don't know if I move too quick. Whenever I write something on the slides, I can see that it's showing up on the screen only about like maybe half seconds late. Yes, any questions?
I do have a question.
Yes, yeah, go ahead.
So let's say, for example, you have an experiment in which you kind of like check weight loss on the same participant. And so in those kind of like studies, you just subtract like the before and after, and then do kind of like a single versus single hypothesis testing. Like, how does that compare to kind of like these examples?
Again, it's I think if you want to base on LRT, it's doable, but because they are dependent data, right? Dependent data in the sense of you are collecting before and after from the same subjects. Right?
Yes.
Is that what you're asking? Yeah. And then, easy way would be you take a difference. You are defining your new random variable as a difference between pre and post. Then that means everyone only have one observation. You see what I'm saying?
Yes.
Right? So of course it looks like a two sample testing. Pre have one sample, post have one sample. Right? But actually, there are so-called pair t-tests already, right? You know how pair t-tests are working, isn't it? Right? So even though we call it like a pair t-test, it's actually nothing but take a difference, then xi yi minus xi, and then testing whether or not the di equals to y minus xi. You're testing about di, whether or not di, the mean is 0, right? So then you might asking me, it's, hey, could I getting stuff around writing down like a function of xi and y? Yes, you could. Okay, you could go with, you could imagine this as, because right now your x and y are not independent data anymore. That means two sample as a dependent data. If I want to write down like a function, how to write? You need to write down your like a function as what? Bivariate normality. Making sense? So that means when you do your LRT, it's your like a function, either numerator or denominator, is a ratio of two bivariate normality. Okay, it's definitely doable. You need to estimate your mu x, mu y, sigma squared, and then what? And your rho as well, in terms of association between x and y's. Okay, it's all complicated procedure. It's still doable, and I guarantee you that that give you more power compared to taking a difference. Did you get that?
Yeah. No, I get it.
Yeah, you get it,
Thank
right?
you.
Yeah. One thing is you get a full like function written down. So of course you're more powerful compared to something you're actually taking out the difference between, it actually taking out the dependence between x and y. Okay, so this is a really good chance for you guys to think about it. But because you guys are going to PhD study, your situation is, I have one hand, I having a procedure which is really awesome, okay, but it's really hard to solve. But it's more powerful, more efficient, and in some sense. But at the other hand, it's, you have really easy testing procedures, okay? Really easy to implement, really easy to interpret, easy to explain it to people. But the point is, if I do that, I'm going to lose efficiency, I'm going to lose power. You have both hands, okay? Should I do either hand? I will tell you no. Either hands all have pros and cons, okay? But sometimes, actually, to tell you the truth is, we are doing more frequently sacrifice efficiency, go with more easier testing procedures. So that's easy to communicate, okay? Which also means that it's, if you're doing your dissertation, you're going with the complicated procedures because it looks like awesome, right? Give you more pages of a dissertation, right? Compared to the easy procedures, right? But you definitely need to have a sense of why you go with the one hand or the other hand. All those pros and cons you need to know better than other guys. Okay, sounds good. Okay, good. Let me go through a little bit about 5 minutes. Go to the so-called. Okay, you also have you don't have to do LRT every time. You really have some really easy choices, like this word test, so straightforward. They are going to talk about it in the 661 as well, but not in this kind of depth. I will bring that up and I'll go through it, and then not necessarily emphasize anything about it. Okay. And then, so if we do testing about this guy and this guy right here, so everything you think about this is what you want to choose, right? This is so intuitive. Why not? I can get information about data. I might choose. Then as long as I can get what my standard error would be in the denominator, I divided it. It follows normal 0, 1, right? Asymptotically. Okay, if it's actually asymptotic normal 0, 1. If I do have less, everything should become easy, follow through, because I do know that it's when n is large and large, my statistic in the left-hand side is going to become normal and normal. Then I just assuming my n is large enough, then I compare to what? Normal 0, 1 is quantile. That's what we'll test it. Straightforward. Okay. But I do want to mention one thing is, hey, could I do this? What's the difference between these two guys? One thing is divided by estimated standard error. Another thing is divided by standard error under null hypothesis. Okay, can I do this one? Yes, I guarantee you it is yes. Okay, because your statistics constructed under null hypothesis. It's under null hypothesis that could give you anything, give any information, you use it. Okay, this guy right here doesn't using anything about, okay? Times this guy right here is not easy to get actually in the real practice. Because I do know what null is, this guy sometimes is relatively straightforward to compute because you don't have to involve in any bootstrapping procedures to get that standard error of theta headed. Okay, and especially whenever this guy goes to P, this guy right here, right? You will say, well, yeah, by Slutsky, they are all normality at the end. Okay, good. So a special list. So I don't have much time to talk about detail right here. Okay, but I want to just jump in through. Okay, so if you really like in the future, if you really do like a machine learning things, you are trying to say, well, I'm going to run ground truths to predict errors, and then I'm going to get data in terms of predicting about you. Okay, so you do have X, Y, and then right here. Okay, you're using the point is the first question would be what? Using different data set. One thing X coming from one data set of size N, Y coming from testing second data set size M. Okay, then if you do a comparison whether or not there's P1 versus P2, right? So you want to know whether or not one algorithm is better than the other. Your null hypothesis P1 versus P2, and then versus alternative. And then what's that other test? Easy, straightforward. Really nothing but what? Really nothing. Let me see if I can see here. Nope. Okay. Okay. Nothing but what? It really nothing but X bar minus, okay? Again, minus theta 0, P1 minus P2. Okay, going back to this, right? Theta head minus theta 0, okay? Theta head, P1 head minus P2 head, okay? Then minus P1 minus P2. Of course, under null hypothesis, this guy equals 0. Then divided by, so square root, the thing right here, square root right here, okay? Square, I'm sorry, standard error, okay? Then how to do standard error things then? It's nothing but what? You do have variance of X bar, then minus Y bar. You're deriving it, right? Equals to what? And P1 minus P1, then plus M, P2, 1 minus P2X, okay? So that means my standard error is going to become square root of this guy's standard error, okay? Then XE squared, just plug in. Easy, straightforward right here. Okay? Then I could give you that in the final exam, to be honest with you. So how do you show that eventually these guys go to D no more 0, 1 then? You should be able to show that at this stage, okay? Using all those skills I teach you about large sample theories, into that, you know, weak, low, large number, and then domain theory is a bunch of things, okay? So let me jump. You know, of course, this is exactly you talk about is what if you're testing in the same testing set, okay? So, okay, it's 3 o'clock right now. You're free to leave. Okay, I'm going to finish. Don't mind, that means finish. Okay. So then, what if you're testing the same data set? Really the same as Jesus talk about it. So what? You do have X and Y dealing with the same sample. Okay. Then in that case, they are not independent sample anymore. the easy way to evaluate, you evaluate the same subject, right? One says it's cancer, the other one says it's not cancer. Okay, or maybe both are cancer, both algorithms says it's cancer. You look at the image of cancer research, of cancer image data, right? So then you can directly take in that difference between xi and then yi. Okay, so one thing I do want to mention is xi and yi basically both are Bernoulli, P1 and P2. That means, so when I'm a student, my professor told me that it's binary variable really behave like a continuous variable. Okay, so any procedure you can do with continuous variable, you can apply that to the binary random variable. It's the same thing right here. You have di as xi minus yi. Okay, then of course expectation d right here, delta right here, that's a p1 minus p2. Under null hypothesis is 0. Under null hypothesis it's. And then what? Then it's nothing. Just do one thing. Is you're using di to do inference. Okay, you don't have to using x and y to do it anymore. Okay, and then you do that, you're deriving the standard error on d. Okay, that means your delta head right here is d bar, using d as a random variable. And then again, like I said, you could just treat your binary random variable as a continuous random variable. Everything will follow through. Okay, then you're deriving your standard deviation or sample variance. The same thing as continuous variable is. Although you can imagine it's what the di is going to be. Di is nothing but what? They agree each other. xi1, yi1, di is 0. xi1, y0, di is 1. Or xi0, y1, di is 0. You even only have three categories of di. If we still do the same thing as Vortex do, then this guy right here, we still can prove, even though di only have 3 values, I can still prove this guy is going to become normal 0, 1 edge when n goes to infinity. Okay, it's actually provable. Okay, good. So I think that's how straightforward Vortex is. So let me ask you one thing. Going back to Jesus' question is, if you really have xi binary, y binary, could you still using join PDF to account for dependence? I will told you it's really hard. We know a lot about binary normality. We know a lot about the dependence between binary random variable. We really know less. I'm not saying know nothing, but know less about dependence between binary random variable. Okay, of course, if you are guys taking a GEE right now, you know how to handle it. Okay, but that's another topic of statistics. So again, we are going to talk about this eventually. I will show that if you have word statistics, it's actually when n goes to infinity, they are identical, they are equivalent. Okay, which means that both statistics is going to be the same whenever n goes to infinity. Okay. Then we will show that in 661. You will know what happens at that time. Okay, just give a heads up for this. Which means that it's LRT somehow difficult to derive. You have easier choice called word test. Okay, but again, you need to sacrifice something because you need to assuming your n is large enough. Your word statistics is more feasible. Okay, good. Again, going back to that finite n or n goes to infinity. So doing testing is the same thing as well. You do need to ask yourself, I do this test, I based on finite n or based on n goes to infinity. Okay. The final thing I want to talk about is permutation test. You guys might heard about that. I don't know how many of you actually do that right now. Okay, so or heard about that already. Okay, but this testing is really some testing. It's really intuitive and really no assumptions. So which means that it's again, I want you guys to have a sense of what you are doing right now. Okay, when you say I'm doing testing, okay, if I'm going to use LRT, you do need to assuming your distribution is correct. Okay, for example, you can always assuming, well, my random variable follow normality. But in reality, is your variable actually follow normality? Possibly not. Especially if you are doing like a clinical science in the future, if you're collecting medical data. You really, of course, you can write down those histograms, right? You can basically just draw a graph to see how normal of my random variable is. But the point is sometimes it's just not normal, just skew, right? So if it's skew, then what kind of tool you have, what kind of weapon you have to deal with this kind of non-normal distributed random variable? Okay, so I don't know if you remember PK Sen, Dr. Sen. He is a really big name of so-called doing non-parametric test. Okay, I mean, it's unfortunate we lose him. He retires. Otherwise, he's the best person to tell you how to handle non-parametric testing. Because for now, we don't have. I mean, we don't have a really good guide to talk about so-called non-parametric analysis. Okay, so non-parametric means that I don't really have to assuming what underlying distribution is. I can still do inference, like a permutation test is. So say if you have x1 to xn, it's f of x. y1 to ym is y, f of y is are two independent samples. Okay. One thing to keep in mind is your null hypothesis is not necessarily writing down like a theta equals theta 0. Your null hypothesis is not necessarily comparing parameters. Actually, the most robust procedure should be written down as your null hypothesis comparing what? Comparing distribution. The reason I said it's more ideal is what? Because if you compare only about means, standard deviations, it's only compared about what? First moment or second moment. But if you can develop a procedure actually testing about a CDF or PDF, that's actually more powerful. I'm not saying it's not powerful. It's actually more ideal. This because if I can testing about whole distribution, that means every moment satisfied, every moment follows. Okay? So which means that you do need to understand your procedure. Are they testing about only mean, or are they testing about standard deviation, or the procedure is actually testing about whole distribution? Okay. So this statistic is actually straightforward. For example, right here, if I have a statistic testing right here is what? X bar minus Y bar. Okay, it is statistics. Okay, how do I deriving p-value without knowing what x1 to xn follows? Okay, you add so-called permutation. Permutation means what? That means you do have your x1 to xn, y1 to ym lined up. Okay, and then you permute it. Permute it is, you could actually write down as what? X2, X1, dot, 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 everything the same, Xn, Y1, dot, 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 to Ym. This is one permutation. You could also permute Y1 first, then X2 second, dot, 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 until Xn, then X1 switch with Y1. That means you basically put your m plus m observations into different slots. You recombine it. Okay? Then how many permutations you have? Nothing but n factorial, n is n plus m. Okay? Good. Then permutation test means that you do have your t right here. It's observed data. You observe it. I'm sorry. It's not capital T. Let me take it out. Okay. I need to take a break now because my brain is still jamming. Okay. You do need to know about observation T right here. It's right here. Or saying that it's, maybe I don't write it. I just write it down right here. It's actually X bar minus Y bar in the case. That's what you observe. Okay. But you don't know about what distribution of your T is. Okay. Everything we do in this class is what? I do normal. I do know that my X1 to Y1 is normality. So I can derive LRT, then until this step to find the color of C, right? Or find p-value things. Because I do know T is followed by PDF. Okay? They are one called parametric inference because you do assuming underlying distribution follows some distribution already. Okay? But right now, non-parametric test is what? I don't know about distribution of T, but I can using permutation skill to obtain an empirical distribution of T. Okay? If I can do so, that means I don't have to assuming what underlying of X1 to Xn or Y1 to Ym is. Okay? As long as I can simulate my empirical distribution of T's, then I can claim that my p-value defined as probability of T bigger than what I observe. The same thing as what the p-value definition is. Okay? By doing so, really nothing but writing down right here. Okay? Writing down right here, this needs some kind of assumption is what? Or let's not say assumption. There's a critical jump between here and here. Okay? One thing is, I do have my permutation. I do know for each permuted sample, I calculate one statistic T2, until Tn factorial. Then I can basically, histogram on T's, right? I can plot histogram on T's. Then I have in that right here is my observed TOBS right here. Then this is my p-value based on how many of them bigger than T observation is. Okay. One thing is critical is what? Is this guy right here is going to be uniform distribution. The reason for that is because under null hypothesis, X1, Xn, Y1 to Ym all follow the same distribution. Of course, whatever no matter how you permute them, right? No matter how you no matter how you put them into different slots, they all having the same chance to become. They all have the same chance to have a new They all have a new chance to become using that sample, the T equates all have the same chance become their value. That means that the statistics actually follow uniform distribution, such that you can using empirical to estimate the true probability is. Okay, so I think that's it. Okay, if you have questions, you could ask me right now. Otherwise, I'm going to stop the recording